Yeah, so welcome to today's algebra seminar. And today we will have a talk by James Macpherson from Norwich, who will tell us about generalizations to infinity in finitary two-representation theory. So please, James.
Thank you for the invite, and hello everybody. So yes, I will be talking about these various generalizations I've worked on. So to start with, before I get into the main body of the talk, I'll give a little history. So specifically, I will start by talking about categorification, where the basic ethos here is if you have some mathematical structure you're interested in, then you create some higher level mathematical structure that encodes that lower level structure. And then generally, higher level structures have extra machinery. So you can use this to derive new information about the lower level structure. The first known example was Kovanov, who categorified these things called Jones polynomials from knot theory as Euler characteristics of complexes of modules, which you can view as elements of some category. The problem, if you want to take this approach, is that a higher level structure is generally much more complex and potentially harder to study and work with than your lower level structure. And how do we solve this? Well, we have a complicated structure. Let's use representation theory to look at it in terms of simpler structures again. So this leads to this concept of two-representation theory. So specifically, we have the representation theory of some variety of two category. That's variety in the colloquial sense I mentioned. So there are various different ways you can come at this. Various authors have done so. So for example, Ettingov and Ostricht have looked at two representations of tensor categories. And then Kovanov, Lauder, and Ruquier have looked at this in the context of Lie theory. And most relevantly for this talk, we have Walter Meesterchap and Messer-Miermitz, who have looked at finitary two-representation theory, which is what, and I will spend the first half of today talking about what that means in a fair bit of detail. So to talk structure, I look at finitary two-representation theory and specifically relaxing some of the finite assumptions that turn up in its definition that I will point out as we go along. So to start with, I will give the overview of this classical theory with all the finiteness assumptions intact. And I will mention some important results as well as some useful examples that turn up. And then the second part of the talk, I will talk about my generalizations. So this is the finiteness condition generalizations, and I will also mention some related work on introducing a grading as well. So if we want to define finitary two categories, it turns out we need to start by defining finitary categories. So the basic idea is a finitary category or two category is a category or two category where we have a significant degree of additive or linear structure. So some notational stuff. We will always work over an algebraically closed field, primarily to make some of our examples work nicely. And we will always be working with strict two categories. There are some subtleties here related to taking strict two categories that I will be skipping over. I will mention them briefly as they come up, but no more than that. There has been some work done in the area by other people on bi-category stuff, but not that much so far. I believe there's only one paper on the subject so far. And most of these initial definitions up to a certain point I will mention are drawn from the initial series of papers by Walter and Vanessa. So a finitary category is an additive, k-linear, idempotent complete category with finitely many isomorphism classes of objects and finite dimensional Hom spaces. And those will be two of the finiteness conditions we'll be coming back to in some fashion. And as a bit of notation, the two category of these with the relevant additive k-linear functors and natural transformations is denoted this AKF. So we have the one category version. Now let's look at the two category version. So a finitary two category is a two category which we'll call C, which has finitely many objects. Again, this is a finiteness condition, such that for any two objects I and j, the Hom category from I to j is a finitary category, hence that definition coming first. Horizontal composition works nicely, so it's additive and k-linear. And as a particular example of indecomposable one morphisms, we want all the identity one morphisms, which we denote with this blackboard bold 1, to be indecomposable. So as an example, this is in some sense the simplest example that I'm aware of that holds some interest in the field. We have this thing called CA, which is a two category associated to an algebra, originally coming from the first paper by Wolf and Vanessa. So we take A specifically to be a basic self-injective connected K-algebra. The connected, I will explain in a bit. The self-injective will turn up in a couple of slides. So the related two category CA has a single object, which we denote generally with a star. And you can think of this as being, in some sense, A mod, so the category of A modules. This is the connected bit. Since A is connected, we have a single object. If it wasn't, we would have one object for each A. I will give an example of this in the second half of the talk related to CA, but you can also do this in this finitary setup with finitely many connected components. So in our one object case, the one morphisms are so technically direct sums of functors with summands isomorphic to, that's just to make things nice and have our additive structure that we want, idempotent complete, etc. So we build them from the identity functor, which it will be indecomposable, and with tensoring with projective AA biomodules. And then the two morphisms are natural transformations, and due to various algebra-related results, we can just think of these as bimodule homomorphisms, up to some strictness stuff, which with the isomorphic there in the definition of one morphisms. And then Vanessa and Walter showed that this is a finitary two category. So now to give a somewhat more complicated example that is nevertheless probably worth looking at, let's look at circle bimodules. So these are a construction that's useful in many areas of maths, most prominently geometric representation theory, but also knot theory, combinatorics, and so on. So they are more complicated, but they are worth defining, and I will be coming back to them in the second half of the talk as well. So to start, we have this thing called a Coxeter system, or a Coxeter group, which is a group W generated by a set of what are called simple reflections. So the idea is these are reflections. So for any of them, S squared is the identity. Probably should have been E there. Yes, that should be an E. No, it shouldn't. Never mind. Yeah, so S squared is E. And for the rest of them, there is either some finite power of SR that gives the identity, or possibly some dubious notation there. That should be Z to the plus. So positive integers or infinity. And if this power is infinity, that just means there is no such relation. So now we take some, I'll just call it a nice representation of the group, technically called a reflection faithful representation, but don't worry about it. And then we take, depending on the setup, either the symmetric algebra on its dual or a quotient thereof, and call that R, which can be given a grading. For this half of the talk, we will be technically working with the quotient, but it doesn't actually matter for the representation theory that's coming up. And so notation, the subspace of R fixed by a reflection is R to the S. And then we have these things called Bott-Samuelson bimodules, which are various tensors over, so it's kind of R tensor over RS1, R shifted by something is a basic one. And then if you tensor those together, it will be R tensor RS1, R tensor RS2, so on and so forth. And then at the end, you'll have a shift by N, depending on how many, if your last one is Sn. And then the category of Sergal bimodules, so this is a one category, is the subcategory of graded R bimodules generated by shifts of Bott-Samuelson bimodules. As I said, there's a grading structure here, so we take all possible shifts. So then the two category of Sergal bimodules, which is the structure we're interested in, has again a single object, which we still associate with R mod. So this is starting to look like a similar construction to CA. The one morphisms are, again, this construction because we need to be strict, direct sums of functors with some ends isomorphic to, again, either the identity functor or now to tensoring with Sergal bimodules. So rather than taking projective bimodules, we're taking Sergal bimodules. And then again, the two morphisms are the natural transformations, which again correspond to bimodule homomorphisms. And as shown in a paper by Tobias Kiltoff, Walter, Marco Mackay, and Jacob Zimmerman, there are a lot of people whose surnames are M or Z, but I believe that's the correct way around. In the case where our Coxeter group is finite, then this two category is a fiat category. I haven't said what fiat is yet. We will get to that shortly. Indeed, we'll get to that here. So we often desire extra structure in our Finitary two categories. So we say that a Finitary two category is weakly fiat if it has internal adjunctions. So somewhat more formally, given any one morphism F in C, there is some other one morphism F star, which goes the opposite direction. And then we have two morphisms from F star to the identity, let's call it epsilon, as well as eta from the other identity for F star F, which obey certain axioms. And these axioms are just the standard axioms for an adjunction. And in particular, a weakly fiat two category is fiat if the dual of F dual is isomorphic to F. So we don't just have internal adjunctions, we have ambidextrous internal adjunctions, or you can call them biadjunctions if you want, but there are, well, you can call non-strict two categories bicategories, and at that point, this is kind of a duplication of notation. So generally, I try and use ambidextrous adjunctions. So we have had these two categories, these Finitary, fiat, or whatever, two categories, which are our complicated structure. We want to do representation theory. So what's the analog of vector spaces in classical representation theory are simpler structures on which our complicated structure acts? And the answer, depending on the setup, will either be finitary or abelian categories. And as some notation, the two category of specifically k-linear abelian categories, we will denote by ab sub k. So then let us take a finitary two category. A finitary two representation is a strict two functor from our two category to the two category of finitary categories. And similarly, an abelian two representation is a strict two functor from C to the two category of abelian categories. Now, saying this is a strict two functor isn't the most illuminating way of presenting the definition. So let's look at that in a little more detail. So we take our finitary two category C, a finitary two representation M of C has, for each object I in C, we take some corresponding object in our target two category. So in this case, that will be a finitary category, which we'll call M of I. For each one morphism, say F, that will correspond to a one morphism in the target category, which here is a k-linear additive functor between, say, Mi and Mj. And then a two morphism goes to a two morphism, which is a natural transformation. And then two separate two representations, M and M, are equivalent. I don't worry about the precise detail of this. Just be aware there is a concept of equivalence. It means there's a two natural transformation between them that induces an equivalence on each component category. Don't worry if you don't know what two natural transformation is. The important point, equivalence will be quite relevant to us going forth. So, in modular representation theory, simple modules or irreducible representations, if you look at them in that fashion, have an important role in the theory. So the question would be, what is our equivalent here? It turns out these are what are called simple transitive two representations. However, their definition is a little complicated to get at, so it will take us a few slides. So let's start with the concept of ideals of two representations. So we take some finitary two representation of a finitary two category. An ideal K of it gives for each object I in our two category a set K of I of morphisms in M of I, which are closed under composition, addition, scalar multiples, and under the action of C. So that's, composition with any morphism and addition within Ki. So the standard construction you'd expect of an ideal. And in particular, when I say closed under the action of C, this means if you take some morphism X in the ideal and a one morphism of C that goes from the right object, then the image of X under M of F remains inside the ideal. So we have this thing we call an ideal. We would quite like it to be justified in calling it an ideal. So as it turns out, it is. We can use these to construct quotient two representations. So we take some finitary two representation with an ideal K. Then the quotient representation M over K has, for each object, this is a two representation, so we have some finitary category M over K of I, and this has the same objects as M of I, and then the morphism spaces are the quotients of the morphism spaces of M of I by the relevant subspaces given by K of I. I'll explain this in a little more detail in a second. And then this is a two representation. We have the action of the one and two morphisms of C, and these are just induced by the actions given by M in the natural fashion. So more explicitly, for this quotient, given any objects x and y in M of I, the morphisms from x to y that live in k of I, which is what this notation is by its construction a subspace of all the morphisms from x to y. And so we can take a standard quotient of vector spaces, and the rest of it follows through. So that is one part of what we will need to define simple transitive two representations. The other part that we will need is this concept of transitive two representations. So let M be some finitary two representation again, and choose some object x in M of I. Then we have this C-span of x with a notation G sub M of x, which is in some sense the smallest sub two representation of M that contains x. So we have this technical definition here. We take the additive closure of all the images of x under one morphisms in C. But this is, in some sense, the standard conception of the sub two representation generated by x, if you think of generated by in various other areas of maths. So then a finitary two representation M is transitive if given any I in C and any x in M of I, the C-span of x is an equivalent two representation to M itself. So whichever caveat, as long as x is not zero, any non-zero x generates the entirety of M. So now we can actually define simple transitive two representations. So transitive two representations aren't quite what we want here, but they do have an important property. And this was proved by Walter and Vanessa in their 5th paper together on this subject. So any transitive two representation, M has a unique maximal ideal that doesn't contain any identity morphisms except for possibly identity morphisms for zero objects. And when this ideal is the zero ideal, we call M a simple transitive two representation. So what this means is, if you unpack various definitions, a simple transitive two representation has no proper C-stable ideals. So if you've got any C-stable ideal of it that's not zero, it will end up, by this definition, it will contain some identity morphism, and then because it's C-stable and because M is transitive, it turns out it contains every identity one morphism, and since these are closed on decomposition, that means it contains every morphism, and thus is not proper. And this is the nice analogy to simple modules having no proper submodules, which gives the indication that this is the proper concept we want. In particular, since I was talking about quotient two representations, every transitive two representation has what's called a simple transitive quotient, where you quotient out by this maximal ideal. So I will take a brief diversion here to talk about the concept of what I call internal versus external. So in representation theory, we often want to reduce external problems, which are potentially very large, a lot of information. We don't know what the bounds of where that information lives are, to internal problems. So where we have a very set, defined boundary for where the information we have to study is, which makes the problem much easier to solve. As a classical example, in characteristic 0, for group G, there are a lot of vector spaces that you could try constructing irreducible representations on. Obviously, one for every dimension, some number of uncountable or infinite dimension ones, and so on. But representations are determined up to isomorphism by their characters. And those characters are in bijection with conjugacy classes of G. And the character is just some map from the group into the underlying field. So this reduces the external problem of classifying representations to this internal, somewhat, problem of finding a known number of class functions on our group G. And a lot of powerful theorems and concepts in two-representation theory follow this same pattern. And the remainder of this first half will be me detailing two examples of this, which are cell two representations and co-module two representations. So let's start with that cell one. So we have this concept of cells in two categories, which are based on Green's cells in semigroups from back in 1951. The basic idea is if we have two isomorphism classes of indecomposable one morphisms, we generally, in notation, ignore that these are isomorphism classes. So we have F and G in a finitary two category. We say that F is below G in the left order, or we also have right order and two-sided order. When there exists some one morphism H, where G is a direct summand of HF. Respectively, for the right order, that would be FH. For the two-sided order, HFK. Note here that F is below G, but G is a direct summand of HF, which is a subtlety. It can be quite easy to get wrong. And then these are pre-orders. They have equivalence classes, and we call these L cells or left cells, and then respectively R cells, right cells, J cells, two-sided cells. And then we will also briefly in this talk come across H cells, which are the intersections of the left and right cells. And a useful fact that I will mention here so people don't get confused. Next slide. If you take some left cell L, every one morphism or class of one morphisms X in L has the same source object. So they all go from some object I in our two category, possibly to various other objects J. So we have defined cells, and this allows us to define cell two representations. So we take some finitary two category, and we take L to be some left cell of this two category with domain I. As I mentioned, common source object. So we can now define a two representation N sub L of C, which is roughly the two representation of C generated by the left cell. So each target category N sub L J is a full subcategory of Cij generated by the composition of some element of the left cell with any other one morphism that it can be composed with from the two category. And then we have a very simple action. So the action of a one morphism is given by composing with the one morphism, and the action of a two morphism is just effectively horizontal composition. So although this two representation isn't transitive, it does have the same property as transitive two representations in that it has this unique maximal ideal, which doesn't contain any identity morphisms. In this setup, they're technically morphisms, though obviously in the original two category, they're two morphisms, except for those for the zero object or one morphisms. And so we have this maximal ideal. So the quotient, by a similar reasoning to previously, is a simple transitive two representation. And this is called the cell two representation associated to the left cell. So this is what, using the terminology from previously, an internal construction. it is entirely defined by information that comes from the two categories. So we would quite like to use this to classify external two representations, at least in certain circumstances. And these circumstances turn out to be strongly regular finitary two categories. So to start with, a two-sided cell in a finitary two category is called strongly regular if the left cells are incomparable under the left order. This is a technical condition. I would say philosophically it's not the most important. The most important condition is that each H cell, so each intersection of a left cell and a right cell, contains precisely one isomorphism class of indecomposables. So effectively, you might have seen in other talks by people in this area, you can form this nice grid structure where, say, the rows are left cells and the columns are right cells, and each box contains precisely one isomorphism class. And then a finitary two category is strongly regular if every J cell in it is strongly regular, so every two-sided cell. So this leads us to the first big theorem I will be talking about, proved by Walter and Vanessa, which is that any simple transitive two representation, so an external concept, of a strongly regular fiat two category is equivalent to a cell two representation. So we have this external concept, simple transitive, and we've shown these are all equivalent to internal structures, cell two representations, which is very useful, reduces work when studying these categories, or these two categories even. So now let us move on to the, okay, let's not move on. Before I move on to the second, this co-module two representations I mentioned, I will talk a bit about this concept called Abilization, which is used a fair bit and which I will be talking about in a slightly different form in the second half of the talk. So abelian categories have very pleasant properties, which I won't bother listing here. You almost certainly know most, if not all of them. But that means it would be useful to have some sort of abelian envelope, so some enveloping category or enveloping two category of a finitary two category. And we can do this with this concept called Abilization. So let's start in the one category setup. So we take some additive category, which I'll call B. Then its injective Frade Abilization, B underline, has as objects the morphisms of B. So this is starting to look like it might have some relation to the morphism category of B. And it turns out there is, in some sense, a relation, but it's not the same, in that the morphisms are commutative diagrams, but you take them modulo homotopy. That is, modulo those diagrams where there exists some q from y to x prime, so the diagonal in this diagram, such that G equals QF. And then Frade proved in the paper where he came up with this that if your category has weak kernels, then B underline is legitimately an abelian category, which is nice. And then any additive functor from the original category into an abelian category extends uniquely to a left exact functor from the Abilization to the abelian category. And the way I can say that this extends is that the original category B embeds into its Abilization as the full subcategory of injective objects. This is why I call this injective Frade Abilization. And we can dually define the projective Abilization, B overline, where the homotopy is the other triangle, so to speak. So popping back here, rather than the top left triangle, it would be the bottom right triangle. And then we have the dual statement of this theorem. So you need weak co-kernels, we have a unique right exact extension, and it embeds as the full subcategory of projective objects. And for our purposes, I will say we can extend the definition to finitary two categories and two representations. This is a bit where strictness comes in. There's a paper by Marco, Walter, Vanessa, and Daniel Tubenhauer, which goes into detail. You do need to do some fiddling to make sure it all works. But for our purposes, just think of this base way of constructing it. So now we move on to this concept of coalgebra one morphisms. So our setup here will now be a fiat two category, so internal biojoints, with a transitive two representation. And we have a notation where we take the co-product of the target categories is this curly M. So this is a one category, standard category. And similarly, C sub I as this co-product over J of the Cij. So we take some X in M of I, then there is this evaluation at X functor, or technically Abilization thereof, from the Abilization of Ci to the Abilization of M, which is, as it says, evaluation at X. It takes some one morphism F to M of F applied to X, and some two morphism alpha to M alpha, and this, since this is a natural transformation, to its component at X. And this functor has a left adjoint. As it turns out, there's various useful results from roughly from module categories over finite dimensional algebras that means this exists. And as it turns out from this MMMT paper, that when you apply this left adjoint to the object X, it has the structure of a coalgebra one morphism in C underline. So what this means is that you have some certain two morphisms which go from, let me get this the right way around so I don't get an algebra, go from X comma X to the relevant identity, and from X comma X to X comma X compose X comma X. And those two morphisms obey the standard axioms for co-unit and co-multiplication of a coalgebra. So it's a coalgebra that's internal to the two category. And since this is a coalgebra, it has a category of co-module one morphisms over it, which we'll call comod of X comma X. And it turns out this has a natural structure of an abelian two representation, which you might not initially expect. It is quite nice. And then it also has a sub two representation generated by its injective objects, which we'll call ing of X comma X. And thus this leads us to the second big theorem from this paper by MMMT, which is that there is an equivalence of two representations of C between M underlined, so the Abilization of M, and this co-module two representation. And further, and most importantly, this restricts to an equivalence between M itself and the two representation given by the injective objects. So again, we have this M and M underlined, which is some external concept. It could be a very wide range of things potentially. And we're saying it's equivalent to the co-module two representation and the injective sub two representation. And these are, again, internal structures. We define them entirely using information coming from C. So I will end this first half by discussing and reminding you of what finiteness conditions turned up to prepare us for the second half. So it turns out there were three finiteness definitions. A finitary two category has finitely many objects, finitely many isomorphism classes of indecomposable one morphisms, and finite dimensional Hom spaces. And the main focus of my work, and main focus of the second half of this talk, will be looking at how we can relax these restrictions. Any questions on this first half?
Are there any questions? If not, then I pause the recording. Okay, so please continue.
Yep. So we have these finiteness conditions, and I will start by just looking at this first finiteness condition, so the object one. So if we relax this, we get a construction I call locally finitary two categories, where we can potentially have infinitely many objects. So now a locally finitary two category is a two category C with countably many objects, such that the rest of this definition looks very similar to the finitary one. The hom categories are finitary categories. The horizontal composition is still additive and k-linear, and the identity one morphisms are still indecomposable. And in particular, when I say countably, I am allowing for either finite or countably infinite. So in particular, all finitary two categories are technically locally finitary two categories. So anything I say here will apply in the finitary case if there is a new covering of the result even beyond the infinite objects setup. And I will return to the early example of CA, but now in the infinite case. So we now take a possibly infinite collection of basic self-injective connected k-algebras indexed by I. So then CA has the objects indexed by the same I, and now each I is associated with AI mod. The one morphisms are roughly the same. We still have this technical direct sums of functors with some ends isomorphic to. But now, rather than just being projective AA bimodules in the one object case, one morphisms from I to J, we take tensoring with projective AJ AI bimodules. And possibly if I equals J, we still have these identity functors. And again, the two morphisms remain the natural transformations, and these remain associable with bimodule homomorphisms. It just now happens to be AJAA bimodules rather than AA bimodules. And as with the finitary case, it is fairly straightforward to show that this is a locally finitary two category. Now, as it turns out, the locally finitary two category setup is a fairly straightforward generalization. So there are lots of concepts that apply with fairly minimal changes from finitary two categories to the locally finitary setup. So we still have locally fiat, locally weakly fiat two categories, and the CA I mentioned before, all the A's are self-injective, so they remain locally weakly fiat. Or sorry, so that locally finitary two category is a locally weakly fiat, more specifically. We still have the concept of finitary two representations, of transitive and of simple transitive two representations, with effectively the same definitions, except for infinitely many objects. Ideals remain the same concept. Frayed Abilization still works, still gives us abelian two categories up to the strictness fiddling. However, there are some areas that have some subtleties. And the most prominent of these is when we are thinking about cells in the two category. In particular, in the finitary case, there are each hom category has finitely many isomorphism classes of indecomposable one morphisms, and there are finitely many objects. So there are finitely many hom categories. So by construction, all left, right, and two-sided cells have to be finite. they are all subsets of a finite set. However, in the locally finitary 2 category, we can potentially have infinitely large cells. As a specific example, for CA, non-trivial left and right cells have cardinality I, so the number of objects, and the single non-trivial J cell has cardinality I cross I. So obviously, if I is finite, then these are all finite, and that's just the finitary case. But when I is infinite, these are all infinitely large cells. So nothing essential breaks, as it turns out, in this situation, but there are some useful tools that do. So an example is this thing called the additive closure of a 2 category. This is a tool that allows, you'll see various papers in the area talk about, for example, a 1 morphism, which is the direct sum of all morphisms in a 2-sided cell. Now, in general, obviously, the morphisms in a 2-sided cell go from multiple different objects to multiple different objects, and thus live in different home categories. However, this additive closure is some kind of enveloping structure where you can legitimately do the direct sum of all of them. And in the finitary case, this is perfectly fine. However, generally, when you have direct sums, it only makes sense to talk about finite direct sums, so sums of finitely many summands. In this case, for example, for the locally finitary, if you've got an infinitely large 2-sided cell, you can't take the direct sum of all the 1 morphisms in it because there are infinitely many. So if you have a proof that relies on taking the direct sum in the finitary case, you have to do a lot of work to work out precisely which 1 morphisms it's talking about, and then kind of justify how you can restrict down to just talking about those. But as I said, it's still a reasonably straightforward generalization. So we can generalize the previous big results from the first half to this setting. So these come from one of my papers, which come with preprints. So any simple transitive 2 representation of a strongly regular, locally weakly fiat 2 category is equivalent to a cell 2 representation. So this now goes to locally and also from fiat originally to weakly fiat. And then also, if C is a locally weakly fiat 2 category and M is a transitive 2 representation, we have, again, this equivalence between the Abilization of M and the co-module category over some coalgebra stemming from a non-zero object. And it again restricts to an equivalence between M itself and the injective sub-2 representation. So this is a nice, straightforward generalization. But in this setting, I also have looked at this idea of adding gradings into the 2 category and seeing what we can say. So we add this extra graded structure. For this section, I will let G be a countable abelian group. And we'll start by an informal definition of this graded version. So a locally G-finitary 2 category, which we'll call C, we'll start off with the base of a locally finitary 2 category, such that there is a G grading on the Hom spaces of 2 morphisms with composition preserving grading, both vertical and horizontal composition here. And then grade shifts of the 1 morphisms which are compatible with the grading on 2 morphisms. So to go into more detail, this grade shifts, what this means is if you have some 1 morphism X, then there are also 1 morphisms X shifted by G for every G in the group, such that shifting by G and then shifting by h is legitimately the same. Note this is an example of being an equals, not an equivalent, as just shifting by g plus h. And then when I say these grade shifts are compatible with degrading, it means that if you start off with some, so we have this notation for component degrees, then the degree g component of the Hom space between some shifts is correspondingly a shifting of the grades of the a different degree shift of the original space with this relation here. Excuse me. So this means that there isn't really any different information in terms of the homomorphisms between shifts as there are between the original one morphisms. And something to note here, in that what makes this, which is why we have this compatible degrading, is that the shift of a one morphism is isomorphic to the original one morphism via the shift of the identity morphism. So we have this graded structure for the locally finitary two categories. What happens when we get to two representations and the various other concepts we are interested in. So it turns out these constructions are defined similarly to the locally finitary base setup. So you can still define weakly fiats, cells, and so on and so forth. And most importantly, there is a way to define G-graded two representations, which informally are finitary two representations of our locally G-finitary two category, which also have grade shifts and gradings that are compatible with those on C itself. And if the G-graded two representation is transitive, we still have this adjunction, so we still have co-algebra one morphisms and their co-module one morphism categories. So now, since we have this co-algebra, but it's now in a graded, well, the Abilization technically isn't a graded structure, but it has, I suppose, components that are graded. So let's look at this in more detail, because when we have graded structures in general, we are often particularly interested in the degree zero component, so to speak. So given a locally G-finitary two category, which we'll call again C, we define its degree zero sub two category, C sub zero, to have the same objects and one morphisms as C, but only those two morphisms which are homogeneous of degree zero. And we can do a similar thing for a graded two representation. It has a degree zero counterpart, M0, and this is a two representation of C0. I'm being slightly sneaky in not saying what type of two representation. And the reason for this is that C0 is, in some sense, not quite as pleasant a structure as you might expect. Because in general, if G is an infinite group, C0 is not a locally finitary two category. You might want it to be because we're kind of forgetting the grading structure on the two morphisms. However, the problem is, in general, for non-zero G in our abelian group, X shifted by G is not isomorphic to X, because the identity will always be taken to be homogeneous of degree zero, because we need composition to respect grading, which means its shift by minus G is not homogeneous of degree zero. It's homogeneous of degree minus G. But in particular, it's not in C0. So in general, C0 has infinitely many isomorphism classes of indecomposable one morphisms, which for our definition of locally finitary is a problem. And it turns out that this is an early example of what I will be talking about later, which are called locally wide finitary two categories. However, for the moment, it thankfully turns out that although it's not technically locally finitary, C0 is still fairly well behaved. So in particular, it has weak kernels and weak co-kernels. And I'm aware I didn't actually mention what that means in the first half. A weak kernel has the same definition as a kernel, except that you drop the uniqueness requirement of the relevant morphism that comes from, obviously, the universal structure. So what this means in particular is the Abilization of C0 is calling this a locally abelian two-category, by which I mean the Hom categories are still abelian. So thus, we have this abelianization, which means we can still construct coalgebra 1 morphisms associated to transitive 2 representations in the degree 0 setup. Because if you remember, the definition of transitive only relied on objects in the 2 representation and the action on those objects of 1 morphisms in the 2 category. And those stay exactly the same in C0 compared to C. So if M is a transitive 2 representation of C, M0 is a transitive 2 representation of C0. So in this case, so we'll take a locally weakly G fiat 2 category and M a transitive G graded 2 representation. And as before, we take an object X in M of I. So we can either look at that as being in M, in which case we have the corresponding coalgebra in C underline, technically, which would denote X comma X. Or we can look at X as an object in M0, in which case we have the corresponding coalgebra 1 morphism, again, technically in C0 underline. I forgot that in this definition. And we call that X comma X sub 0. And as it turns out, the useful thing about these two is that since X comma X 0 lives in C underline, lives in C0 underline, but is a 1 morphism, you can still look at it as a structure in C underline as well. And in that setup, X comma X 0 is isomorphic to our original X comma X. What this means is if we have this setup with some X in Mi, again, non-zero, we can choose a representative of the isomorphism class of X comma X in C underline, which has structure maps homogeneous of degree 0. What this means is if you think back to the definition of Abilization, X comma X is a 1 morphism in C underline, which means it's a 2 morphism. Specifically, its structure is 2 unmorphisms and a 2 morphism between them. And that 2 morphism can be chosen to have components of degree 0. And then the co-unit and co-multiplication, which are composed of some number of 2 morphisms from our original category, can be chosen such that all those 2 morphisms are also of degree 0. And the main application I've looked at for this is this things called cycloatomic 2 Catmood algebras. Now, I'm not going to go into full detail about the definition of these because they're somewhat complicated and would take quite a while. But very roughly, a cycloatomic 2 Catmood algebra is this 2 category U sub lambda, which has objects, which we refer to as weights, which form an n-dimensional lattice below some maximum object called the highest weight, which is, as it happens, the capital lambda in the notation. Then the 1 morphisms are generated from EI, which in some sense means going up in dimension I between 2 objects or 2 weights, and the FI, which are down in dimension I, again, between two objects, subject to relations that we derive from Catmood algebras, hence calling these two Catmood. So, for example, for I not equal to j, fi ej is ej fi, and when they are equal, ei fi is equal to fi ei with a direct sum of shifts of the one morphism. I won't go into details. And I'm sure some of you who know about Catmood algebras know that I'm also missing half of that definition, but I'm also not mentioning that. And then the two morphisms are nice enough for all the preceding theory and all the following stuff I'm about to say to work. So as I might have implied from talking about shifts of the identity, one morphism, two Catmood algebras are graded over Z. This is also why I was just talking about countable abelian groups in the previous section. It is possible, I think, that you could do much of this using general groups or possibly even monoids or possibly even uncountable, some stuff. But this was the primary example to work towards, so I restricted it to make it nice, somewhat simpler to work with. And as it turns out, you can show that U sub lambda is a locally Z fiat two category. So it has a nice structure. It has biojoints. So Fi is biojoint with some shift of EI, technically. And then it thus turns out that any simple transitive two representation of U lambda is a graded two representation, so Z graded, and is equivalent to a cell two representation. So this is quite a nice result. We can classify all the simple transitive two representations in this case. So now I will move on to the final
part.
James,
sorry, I have a question. Can you please go to the, so this UA, what is the cell structure? Is this a strongly regular case or not?
Yes, it is a strongly regular case. I just didn't happen to mention it here.
Okay, thank you.
Yes, so the final part of this talk, I will be looking at dropping all three finiteness conditions. So to recap, that's not just the finitely many objects of the locally finitary case, but also the finitely many isomorphism classes of indecomposable one morphisms and the finite dimensional Hom spaces. So can we do this simultaneously? And it turns out the answer is yes, to a reasonable degree. So this is what I call wide finitary or locally wide finitary two categories. But to start with, again, when we define finitary two categories, we started with Finitary categories. Here we will start with wide finitary categories. So a category is wide finitary if it is an additive k-linear and now Krull-Schmidt category with countably many isomorphism classes of indecomposable objects, and where the morphism sets are k-vector spaces of countable dimension. And then we have the two category of these, which is AK, now WF. So the question is, why am I adding in this Krull-Schmidt here? So first of all, it retains the idea that if you're looking ahead to the two category setup, any one morphism is a finite sum of indecomposable one morphisms, which is useful. But also, so that's kind of half of the definition of Krull-Schmidt. The other half is saying that the endomorphism algebra of any indecomposable one morphism is local. And it turns out there's a fair bit of theory in the finitary setup, such as just being able to define cell two representations, which is a fairly kind of basic concept to look at in this, heavily uses endomorphism rings of indecomposable one morphisms being local. It turns out some way back I mentioned a theorem, the unique maximal ideal such and such. That relied on, or at least the proof that turns up in Walter and Vanessa's work relies on this local property. And if it doesn't, you have the idea that you might not have a simple transitive quotient, or you might have multiple. It's kind of, I haven't looked into this much, but it is not a pleasant setup to be looking at. So we keep Kohl-Schmidt so that we keep this local part of the definition. So let us now look at the general definition for locally wide finitary two categories. So a two category C is locally wide finitary if it has countably many objects. For any two objects I and j, the Hom category between them is now a wide finitary category. Horizontal composition, biadditive and k-linear, the standard, so it works nicely, part of the definition. And we still want the identity one morphisms to be indecomposable. And then if you have a wide finitary two category, a wide finitary two representation is a strict functor into AKWF. So the same idea as a finitary two representation in finitary two categories or locally finitary two categories, but now the target categories are wide finitary. So the motivating example, if you recall, Sergal biomodules, and the two category of them, that was a fiat two category only when the Coxeter group was finite. So now that we've got this locally wide finitary two category setup, it turns out we can go much further. And so as I proved in my second paper, the two category of singular Sergal bimodules, don't worry about that, that's a somewhat technical thing, associated to now any Coxeter group with a finite set of simple reflections is a locally wide fiat two category. So this expands massively from the so-called finite type with the finite group to affine type and possibly even wild type Sergal bimodules as being approachable by this theory. Yeah, that's what I just said. Which is potentially very useful going forward. However, this is a much more complicated setup than the locally finitary case. There are certain concepts that do generalize nicely. So, as you might have guessed from the previous couple of slides, fiat and weakly fiat still hold. Transitive and simple transitive two representations still, now that we're assuming local from Kohl-Schmidt, can be reasonably defined, as can cells and cell two representations, and then obviously the ideals. However, there are a lot of concepts from finitary and locally finitary two representation theory that break if you try and naively generalize them. To give a fairly kind of baseline example, the most natural generalization of CA, where you might think, oh, just relax, kind of the minimum to allow this to work, it turns out that the endomorphism algebras of the identity one morphisms are in general of uncountable dimension. And if you remember, the definition only keeps countable. So to define the correct analog for this needs some careful work. I won't go into details for those of you who know some more. It's a C sub A comma X type thing where you require X to be local and to contain some other subalgebra. But for anybody who is less familiar with this theory, don't worry about it. So the remainder of this talk will focus on fixing these generalization problems, specifically regards to these co-module two representations. Because another thing that breaks is this frayed abelianization. So as a reminder, for an injective or projective trade abelianization to produce an abelian category or two category, we need weak kernels or respectively weak co-kernels. But the problem is, in general, the Hom categories of locally wide finitary two categories do not have weak kernels or co-kernels. And the C0 as defined earlier in the graded setup is, as it turns out, an exception that does. However, most of them don't. So we need to find, if we want to keep this nice abelianization setup, we need to find a more general abelianization process. And it turns out the solution was constructed by Edelman in a 1973 paper. So if we take, again, popping down to the one category setup now, an additive category C, its abelianization, it now has as objects pairs of composable morphisms. So x2 for x1 for f1, and then f2 from x1 for x3. And now morphisms are commutative diagrams of this structure, and now again modulo homotopy, which looks closer than previously when I mentioned homotopy to what you might think of when I say homotopy. So modulo diagrams where there exists two diagonal morphisms for these two squares in the same direction, so x1 to y2, x3 to y1, such that the sum of the resulting two triangles is equal to this middle morphism. And again, technically you have to do some strictness work here for the two category setup. But what is nice about this definition is that for any additive category, this abelianization gives an abelian category. It does not put any more conditions than just the original category's additive. And now if we have an additive functor into an abelian category, this extends uniquely to a follow-on exact functor from the abelianization to D. So, as I said, we can again extend the definition up to strictness fiddling to locally wide finitary two categories and wide finitary two representations. However, unlike the finitary and locally finitary setup, this isn't enough. And we need to be able to do more. So the problem is that in the finitary case, we construct the algebra 1 morphism using a left adjoint of this abelianized evaluation functor, which by various theory based on this specific setup exists. But in the wide finitary case, we have no such guarantee. We don't know that just taking this abelianization has an adjoint. We know it's exact, but we don't know more than that. However, there is a solution, and that is pro-categories, or technically pro-two categories. So I will briefly go over the definition of this, if any of you haven't heard of it. So pro-categories, and technically the original paper focused more on their dual, which is in categories, were first introduced by Grothendieck and Verrier in somewhere in SGA, tome 4, expose 1, if I remember correctly. Obviously, SGA is quite large. So roughly, the pro-category of a category is the free completion of that category under co-filtered limits. I won't go into details, but you can look it up if you want. Which means we can now carefully generalize this definition to two categories where we take the pro-categories of the Hom categories. Again, this is another setup where strictness means we can't just go, oh, you take the pro-categories of the Hom categories and then fiddle it so composition works nicely, because you need to make sure that associativity is strict. So you have to actually formally define how everything works from first definitions, and then go, yes, this does what we want it to. And the important result we want from SGA is that a functor f from C to D is right exact if and only if the pro extension of it from pro of C to pro of D has a left adjoint. There is a way, I won't go into details, but given a functor, you can extend it to a pro functor. And this brings us to the final big result. So if we now take our abelianized evaluation functor in this wide Finitary setup and take the pro functor of it, which now goes from the pro category of the abelianized category of CI to the pro category of the abelianized category of M, we can guarantee that this functor has a left adjoint. We will give it the same notation, x comma blank. And the image of M under this has a structure of a 2 representation of C. And then, as it turns out, there is an equivalence of 2 representations of C between M, that's the type of that should be X, and X comma M. So technically, we still have that X comma X is a coalgebra one morphism now in the pro-abelian 2 category, and we still have its co-module 2 representation, and X comma M is some sub 2 representation, but at the moment, precisely what that sub 2 representation looks like as a fully internal definition is not something I'm aware of. It's something I'm looking into, but it is a lot more complicated than just the injectives as it was in the Finitary and locally Finitary case. So I have finished a tad early, but that is all I have got for today. So are there any questions?
Yeah. Thank you very much. Thanks. Thank you very much for, yeah. Are there any questions from the audience?
Well, so my question you kind of already answered a bit, but I was wondering somehow where the countability of was used rather than just any infinite.
It's used, so the reason I would generally give in a formal setting would be all our examples that I know of are just countable. Informally, it might work, but it's like saying countable gives you obviously an upper bound, you know, it's not uncountable. There's a guarantee it will behave nicely. I don't by myself know enough about set theory to guarantee that for uncountable. It's quite possible that most, if not all of this, will work with uncountable, but I didn't. Again, these are 2 papers that came from my PhD thesis.
Right.
I didn't fancy at that point trying to spend the time diving deep into set theory to work out, is there anything that's going to break? So
right.
It probably works fine, but I haven't looked at it.
Yeah, I was just wondering if there was some specific place where here somehow countable is really used explicitly.
Not that I'm aware of yet.
Okay.
Other
Yeah,
questions?
I don't have any examples, so I don't know if it's relevant, but I was just curious if there was some specific point.
Other questions?
Go ahead, Julian, sorry.
No, please continue.
Okay, so the problem you mentioned about direct sums in this first generalization, I believe, that you can't take direct sum over a cell. Could you now fix this via going, instead of the pro completion, to the ind co-completion, where you have the infinite direct sums to work with, and make a statement about the ind extension of the 2 representation?
You probably could. However, most of the time when proofs use this, when I said it was just a useful tool, what I mean is when proofs in the various Finitary papers use it, it's not as in an absolute solid kind of irreplaceable part of the proof, it means that there is some finite collection of one morphisms in here that work. And rather than spending a ton of time in notation identifying precisely which they are and justifying why it's those ones rather than some other ones, you just take the entire sum and go, well, something in here is going to work. So you could do something with incompletion, I'm sure, but it's generally easier to just look at the proof and go, okay, what under the surface is this actually doing? Which unpleasant notation is it avoiding by doing this? And then just sticking the unpleasant notation back in and doing it that way.
Yes, but do I understand correctly that both via pro-completion and inco-completion, you can restrict back to some of the original thing that, the original 2 category and
the original 2 category does embed, specifically if we're taking the Adelman Abilization, you embed into the Adelman Abilization as the subcategory of injective projectives, and then that embeds into the pro category or 2 category as, let's see if I can remember this off the top of my head, the representables, I think, is what it's technically called. But yes, there is a natural way to look at the embedding. I suppose in some sense, an object goes to the trivial diagram of just the object and the identity. So there is an embedding. You could potentially go there, do stuff there, and then come back. But it feels like that would be, in the Finitary case, or the locally Finitary case specifically, that will be a lot more effort than just doing things with uglier notation.
Yeah. Okay.
But yes, that's the kind of thing that might be useful in some points in the wide Finitary. I would have to see what happens as I continue looking at this.
Thank you.
Julian?
Some of the way I've encountered incompletions in the past was somehow in context of length categories and somehow categories of finite dimensional modules over co-algebra, or finite dimensional co-modules over co-algebras. Is there some relation, or at least philosophical relation, to your work?
Not that I'm aware of. I will admit at the moment these are here entirely for that pair of propositions there. It's possible that there is some reason. I know, for example, in the tensor categories book by Egno, they mention at some times that they use ind or pro, or kind of ind or pro categories as somewhere in the background. So it's possible there is kind of a fairly large overarching theory using pro and ind categories as a more canonical setting or some sense for this, where you can do a lot of work in lots of different areas. But in my case, I'm mostly using these because I have to guarantee the adjoint. And the adjoint gives us the co-algebra, which is sufficiently powerful that it's worth the extra faff.
Thanks.
Any other questions? I have a small question about Adelman completion. So the original category, it embeds into Adelman completion, does it?
Yes, yes, as the projective injectives.
So these are the projective injectives, I see.
Yeah.
Okay, thank you. Then I stop the